Hello everyone, my name is Noel Cressy and I'm very pleased to introduce the 2025 Data Science and Statistics lecturer, Professor Howard Bondell, Professor of Statistical Data Science at the University of Melbourne. A little bit about Howard. He received his PhD in statistics from Rutgers University in 2005 and then moved to North Carolina State University. From there, he moved to the University of Melbourne in 2018. He has been an ARC Future Fellow, and he is, though, a Fellow of the American Statistical Association. His research interests include model selection, robust estimation, regularization, Bayesian methods, and all aspects of modeling and handling uncertainty in statistical and machine learning. The title of his Data Science and Statistics lecture this year is Data and Decision Making, Informative Missingness, Recommender Systems, and Personalised Medicine. Over to you, Howard.
Thank you. So it's great to be here. It's my first visit to Wollongong, so thanks for inviting me, and it's my pleasure to give this talk. So the talk itself will be very kind of high level. It's going to be, I don't think I have a formula in it. I took all the formulas out, so very high level, more of the ideas of statistical thinking in some of these more machine learning decision-making problems, where oftentimes computer science, for example, uses it more algorithmically, but I want to inject some statistical thinking into some of these problems. So let's see, there we go. So obviously you see the title, and it'll become clear the common theme of decision-making and the different buzzwords that are in there. You'll see where they fit in. So it's really two different talks. So the first part of the talk is going to be looking at recommender systems. So informative missingness, in fact, in recommender systems. The first thing I'll talk about is obviously what is a recommender system, some common approaches, and then how I deal with this idea of informative missingness. And then I'll give an example. The second part of the talk will be about optimal treatment decisions in personalized medicine. And obviously I'll talk a little bit about that. And the important point there is looking at selecting of variables that are important to include in the decision, okay, and an application. Okay, so the first part, again, informative missingness and recommender systems. And so I'm going to start with this little motivating slide here. So this is back in 2009. Netflix offered $1 million in a competition to predict user ratings of movies. This is a picture of the winning team with a giant check for $1 million. So basically what they did is they provided data on ratings for 480,000 users, 180,000 movies. On average, each user had about 200 actual rated movies. And the goal is everything else, all the missings, to predict those ratings. Okay? And so they actually had the data, so it was like they actually had the test set there. And the prize went to the team with the smallest error on the condition that they also beat Netflix's current best method by at least 10%. And so that team there was the winner. There were two that did the 10% decrease on the Netflix best method. That was the one that did the best. I believe they were from University of Washington in Seattle, a group of them. Okay, what is a recommender system? Well, basically recommender systems are methods that take historical preference data and then they recommend the items to different users. Common example is obviously the Netflix, the movie. So I want to say, okay, you may like this. Right? Ideally, one that they're going to like. Right? So you can think of this as a mathematical, statistical, machine learning problem, just overall arching in various contexts. And the problem is this: given a matrix, a very large matrix, so in this case, we've got users as the rows, movies as the columns, and the entries are the ratings. And usually about 95% of the entries are missing, so a very small number is actually observed. And I want to predict the missing values. Okay, so that's the mathematical statistical problem. So here's a very simplified version of what I'm talking about. The real data is going to be a huge matrix. And the idea is, well, those question marks are missing. Typically, like I said, 95% of it is missing. So, but if I can fill in those question marks, then I know what I want to recommend to the users. Okay? So that's the mathematical problem, is how do I fill in those question marks? So there's sort of three main classes. Okay? And obviously there's lots of crossover, and there's been lots of work on this over the past, I want to say 25 years or so, but there's still ongoing work in this. The first class typically comes from more of a pure math aspect, and it's really looking at the matrix decomposition. So you have this giant matrix, and you just want to do what's called matrix completion. Okay? So you want to do some sort of low rank decomposition and complete the matrix. Okay? Coming from the computer science point of view is what's called collaborative filtering. And basically, you predict via similarities in the space. Thinking about it from a statistical point of view, you have more of a modeling framework, a regression modeling. So you kind of model those responses directly. Right? And so I'll go into each of these in a little bit more detail. So the first one, the matrix completion problem. So you basically, the problem is you want to look at a low rank matrix. There's a simple structure in this giant matrix, matching the observed values as close as possible, subject to a low rank, say rank K restriction. Right? So it's a very simple matrix. There's other restrictions you can put in, but the simplest case is just, I want a simple, smooth matrix. There's many other problems associated with this, but one of the big problems associated with this is what's called the cold start problem. So I get a new user or a new movie. They weren't in my matrix before. So what do I do with that? All right, so there's nothing you can recommend to that new user because they weren't in your matrix. Okay? And so that's one of the problems with just doing strictly matrix completion. Right? Collaborative filtering, on the other hand, is you basically want a user item pair. You find all the users that might already have rated that item, and you compare them to the current user, and then you predict via similarity. Right? So you could do things like nearest neighbors, kernel weighting, various things like that. How close is this new user to existing ones that rated it? Okay. I'm going to talk a lot more about the regression model because that's the approach that I'm going to take. And so the regression modeling itself is not new, so the idea here is I have a specific cell in the matrix. Right? So I have a user rating for a specific movie. And the rating, I'm going to model it by saying it's a function of the features, and I'll talk about what features in a minute, plus a user effect, plus a movie effect, plus an error term. Right? So I've got fixed effects, which are the features. Right? So examples are age, sex, various things like that. I've got features of the movies, which could be the genre of the movie, box office sales, things like that. And the function that I'm going to use, typically linear, but it doesn't have to be linear. It could be nonlinear. And so I'm going to use a function of the user features and the movie features to predict that cell. And then I have random effects. I have a user random effect. Basically, there are going to be particular users that always rate things high. Right? They give everything a 5. Right? Other users, everything's low. They give everything a low number. So that random effect of the users to account for that. And then I have a movie effect. Well, on average, this movie always scores high. On average, this movie always scores low. So there's a movie effect. And then obviously error is everything else that's not accounted for. Okay? The problem, and this is where the informative missingness comes in, and this is never acknowledged, particularly in most of these methods because they come from computer science, for example. They don't think of it in a statistical framework. The data is not missing at random. I didn't tell this user, sit them down and say, watch this movie and put in your rating. Right? The users are going to most likely pick movies that they think they'll like. Right? So the observed ratings are typically on average going to be maybe higher than an average rating, right? Because they've been chosen. It's sampling. It's a sampling bias going on there. And so the actual missingness could have some dependencies on the unobserved rating, right? And so if you don't account for that fact, which typical approaches don't, you're going to end up with biased estimates. More importantly, in this problem is prediction, so you're going to end up with biased predictions as well. Right? And I'll give you an example here. So this is the example I'm going to use later. It's not the Netflix data. It's called the Movie Lens data. It's actually publicly available data. It's a smaller data set that I'm going to demonstrate here. There's a bit over 900 users, about 1,700 movies, and about 6% are rated. And what I'm plotting here is just some preliminary data that I look at for every movie. I look at the average rating of that movie. That's the y-axis. And on the x-axis, I have how many times that movie was rated. And what you see there is a nice linear upward trend showing that on average, as a movie is rated more often, its rating is higher. So that's exactly that kind of sampling bias that I just talked about. Right, so this is just a demonstration of that. Okay, so what I'm going to do here, there's nothing fancy about what I'm going to do next. It's actually just building that into the model. Right? So I'm going to model the informative missingness. Again, I'm using a shared variable approach. So I'm going to call this value in quotes. So there's an unobserved value, and that's the continuous variable. I'm using a continuous underlying value just to make things easier for inference later. So there is a value of the movie that determines whether or not it's watched or rated. And basically all I observe is it's thresholded, right? Whether the value, if that value is greater than 0, it's not missing. If it's less than 0, it's missing. And I model that value as a function of the rating, right? So there's some function of the rating, plus again a user effect, a movie effect, and an error. And again, I could put linear in the examples later. I'm going to have it's linear in the rating. So basically what I'm looking at here is the probability of rating the movie is monotone in what that actual rating is, right? It's modeling that graph on the previous page. Now, the user effect and the movie effect are random effects here again, but they actually are different. They model different aspects, right? So here, the user effect accounts for just people that watch a lot of movies, or rate a lot of movies, right? Because remember, this is the probability of the movie actually being rated, so not missing. So the user effect here is not people that rate high, it's people that watch a lot, rate a lot. Right? The movie effect are things, popular movies, ones that are rated and watched often, or unpopular movies that are not watched often. So it has a different, still a random effect, but it has a different type of effect. Okay. So basically what I've just talked about is a joint model. Right? So I've got a joint model for the rating and the missingness together. So again, this is just showing the model I talked about before. So I've got the two models, the one for the rating and the one for the missingness, which depends on the rating. Right? And then it's thresholded. If that continuous value is above 0, then it's observed. If it's below 0, it's not. And so the idea now is there's feedback between the two layers, right? Because the model for the missing values actually contains the rating. The other thing that's in here, I'm not going to go into details, is there's also a low rank latent factor model into the error matrix. Basically what that does is there's some structure in the error matrix. So imagine if you think about I talked about the matrix decomposition methods before. I'm essentially doing a low rank matrix decomposition on the errors here as well in the random effects. Because I don't want to put movie times user effects in for everything because matrix is too big. So I'm just doing a low rank thing on that. I'm going to assume normal distributions for everything, for the random effects and the errors, which basically gets to a probit model for the missingness. Right? And you don't have to assume normality here. I'm doing that for simplicity of estimation and things like that, and inference in general. Okay, so how do I fit this model? Well, given this joint model setup, the natural thing that I could do here is an EM algorithm, because I've got everything conditional, everything or it's either normal or truncated normal, things like that. So I'm going to do EM. Alternative, I could do a fully Bayesian approach. Right? Everything is conditional conjugate. So I could do either one here. It's pretty agnostic onto what method of inference you use. The goal, at the end of the day, the goal is not the estimation part, it's the prediction part. Right? Remember, the problem in the beginning was to talk about, I want to do recommending of movies, which means I need to do the prediction of the missing cells. So how do I predict the ratings? Well, conditional expectation is what's normally done. So the random effects, you do conditional expectations in there, right? Best linear unbiased prediction, those of you that are familiar with that, right? But the idea is, the reason this works is, given the joint model, if I condition on a rating being observed versus conditioning on it being missing, I'm going to get different predicted values. Because that joint model, there's feedback between the two layers. So the intuition is, all else equal, if I predicted a rating that was actually observed, it's going to be larger than one that was missing, right? If everything else was equal. Okay, so now I'm going to go through that example. So the movie lens data that I gave that little teaser in the beginning, it's available online. And so this, again, it's not a bit over 900 users, about 1,700 movies. It's about 1.5 million cells in the matrix. Right? Just multiplying that out. And there's about 100,000 that are observed, so about 6% observed. So I've got about 100,000 actual observations in a 1.5 million size matrix. Okay? And the covariates that are available in this data, I've got age, I've got sex, and I've got postcode, the first digit of the postcode. This is US data. So first digit of the postcode, age, sex, and occupation. It's a categorical variable. So that's for the user, and for every movie, the only covariate that's here is the genre, so categorical movie, the categorical variable for the movie genre. Okay. And there is actual a split in the training set, an existing split. So I've used that, but I've also done multiple splits. So 80% of the data for training, and then 20% for test. Okay. And the only comparison I'm going to do here is fitting the full joint model, so incorporating the informative missingness versus not using the informative missingness, but using the same regression model. Okay, so just what is the benefit of including that informative missingness? This little throwaway sentence there took a really long time to really wrap my head around. So if you remember, I said I've got 20% left out for the test. So I want to predict on that. So, but you have to condition on something. So you would think, well, I condition on the fact that it was missing. Well, actually, no, it wasn't missing. I removed it. It was there. So for this example, you actually have to condition on the holdout data actually being observed. The data that was actually missing, you would condition on it being missing. But the holdout data, it was actually observed. I just removed it. That took a while to wrap our heads around when we were working on this. So what I've got here is box plots on, so basically I've got, so this is just on the one split, the split that's existing in the online. So there's approximately 20,000 data points that are left out, that are pulled out. It's 80,000 training, 20,000 that are there. The mean squared error for the full model, if you look on the left, the mean squared error was 0.95. Mean squared error for including the informative missingness was 0.81. Is that a big difference? Well, it's more than 10% improvement. 10% improvement on the Netflix data was worth $1 million, so 10% improvement is probably pretty good. With that in mind, this isn't the Netflix data, and it's not against their best method, but just to give you an idea that 10% improvement is a reasonably significant amount. Okay? So that was the first part of the talk. So I've got details. If we want to talk about it later, I've got a little bit more details of the actual math behind it, things like that. But the intuition is, right, so you include the missing data mechanism, thinking about it from a statistical point of view, it's going to improve your accuracy, hopefully. But at least, even if it doesn't, it's modeling things in a more appropriate way. Right? For larger problems, remember, the one I looked at was 1.5 million cells. That's very small in this context. Right? The Netflix data was 480,000 by 180,000, so a lot more. You could do a lot of divide and conquer type things. There are ways to parallelize this. And obviously, it can be used with other recommender systems, products, music, various things like that. Some additional structure that you might think about is, ideally, the probability of watching a movie is monotone in the true rating, right? Because you chose to watch that movie. You think you'll like it. But actually, people don't always rate everything. So there is a difference. So in this data, all we have is whether they rated it or not. We don't have separately whether they watched it and then rated it or not. Ideally, you think about human nature, you watch something, most of the time you're not going to rate it. If you really, really loved it or you really, really hated it, you probably wouldn't, right? So ideally, there is a conditional, like given somebody watched a movie, the probability that they rated it is actually more quadratic-like, where they're more likely to rate it if they really liked it or they really hated it. That we don't have that data, right? But that would be an interesting another level where you've got they watched it and then they rated it, and there's two different structures going on there. So that would be interesting if that data was available, but as of right now, as far as I know, it's not. Okay, so that's the first part of the talk. The second part, I'm going to talk a little bit about optimal treatment decisions in personalized medicine. So this is a bit related to what Sumit talked about earlier in terms of Markov decision processes in a very simplified version. So I'm not talking about sequential decision making here, just a single time point kind of thing. Okay? So personalized medicine, so what is personalized medicine? So if you look at this picture, basically you look at the color coding on each individual. So I've got a bunch of patients here. The color coding sort of says what is the optimal treatment to give them. Right? I can give them sort of a green, I can give them a combination, I can give them a purple. And so suppose I just give everybody the green. I'm going to have some people that it works really well. Right? I'm going to have some that it doesn't really do anything for, and some that it might even have an adverse effect. Right? If I could do some analysis and figure out what's the best treatment to give different people, and I gave everybody the optimal treatment, everybody's going to have a positive effect. Right? Or at least most people, but I'll have a much better chance of getting positive effects if I can tailor the treatment to the individual. Okay? And so that's kind of what we want to be able to do. And so, kind of in words, again, the same treatment's not always best, but how do I decide which treatment to give which patient? So it's going to depend on characteristics of the patient, right? Age, sex, medical history, genetic information. Could be thousands and thousands of, gene expression data, whatever it might be. What are those characteristics? And collecting and storing all that can complicate the decision process, add costs. What's the goal of what I'm going to be doing is not necessarily estimating anything about the predicting treatments or anything like that, but it's looking at identifying those characteristics or variables that are important to make that treatment decision. Right? So which of those potential variables should I measure and use as my decision rule? Right? So it's a variable selection problem in a very specific context. So the example that I'm going to use is a clinical trial. So it's an AIDS clinical trial. It's a randomized clinical trial, and it's looking at comparing treatments. It's just a standard clinical trial. There's 16 baseline covariates here. So it's just a single time point that I've got. 16 baseline covariates, age, sex, previous history of treatment. There's 16 of them total. And this is looking at, so the endpoint is 96 weeks. What is the, they're looking at the CD4 cell count relative to baseline. So higher is better. Okay? They want to keep it high, so keeping it relative to baseline around 1 or increasing is actually good. Right? And so there's sort of 3 treatments here. There's the one that's AZT, and then there's 2 comparable treatments where it's using AZT plus something else with it. Right? So there's the 2 treatments that we're going to be interested in are the last 2, which are the combination treatments. Okay, so we're really interested. I'm simplifying things down here to comparison of 2 treatments. Right? The idea could generalize to more, but I'm making things simple here. We're going to compare the bottom 2 treatments, which are the 2 combination treatments. And overall, the AZT plus DDL is slightly better, but it's within standard error, so it's not. So if I had to say what is the best treatment overall, that would be the one, but it's within standard error and they're similar. But the idea is, maybe there's some subgroup of patients based on their characteristics that would actually benefit from the other combination, and then overall I would do even better. Right? So the key here is to think about, when I say variable selection for treatment decisions, it's a very different variable selection problem than standard variable selection problems. Because standard variable selection problems are looking at, you've got a model, and I've got variables that are going to help predict the response, right? So I've got a linear model or whatever type of model I want, and usually you look at the coefficients in the model, and okay, those that have no effect are unimportant, right? That's not what we're looking at here, right? We're looking at which variables help determine the treatment to employ. It's not predicting the response, it's looking at determining treatment. So it's a very different variable selection problem than typical. And here's an example of what I mean by that. So here are 3 potential variables, x1, x2, and x3. And each of them, say, it's a continuous variable, takes the value between 0 and 1. So if you look along the x-axis on each one, there's the values of x. And R is basically the response here. Ignore exactly what R means, but it's the response. It's like the Y, say. And that also goes between 0 and 1. And if you look at each variable separately, for example, let's look at this simply in a simple way, just each variable separately. Okay, look at x1. And what I'm plotting here is a equal 1 is, say, treatment 1, and a equals 0 is treatment 0, say the baseline. And so what I'm looking here is, this is the relationship. As I increase x1, looking to the right, both, whether I gave you treatment 0 or I gave you treatment 1, they're both increasing. Right? So as the value of x1 increases, the response, so the response R, is increasing. x1 is a good predictor of the response. Right? There's a non-zero slope. If I were to do variable selection in a typical way, x1 would be important because it's important for predicting the response. If you look at the second one, there's an interaction, essentially, right, between x2 and the treatment. Right? There's different slopes in there. But if I still had to tell you, so for example, if I asked you, based on x2 alone, which is the better treatment, let's assume higher response is better. For x2, well, treatment 1 is always better because it's always above treatment 0. But now if I look at x3, and I were to ask you which is better treatment based on x3, you would then have to say, well, what is the value of x3? Right? What value of x3 are you talking about? So x3 is different than the other two, right? If I'm in terms of not predicting the response, but in terms of thinking about which treatment is better, x3 would be the only one that you'd have to ask, what's the value of x3? So in terms of looking at all three of these variables, all three of them would show up if you were talking about traditional variable selection, because all three of them are important for predicting the response, but only one of them, x3, is actually important for deciding on which decision, which treatment to make. Okay? And that's the key takeaway here, essentially this picture. So I'm not necessarily going to talk about notation here. I've taken the notation out, but I'm going to talk a little bit about like what is the objective. So the optimal treatment is the one that maximizes the expected response for that patient, right? And so the decision rule is going to be a function of the set of variables, right? So in that case, I had x1, x2, x3. So the decision rule is going to be a function of x1, x2, and x3, right? And what I want is what is the decision rule that results in the optimal treatment for each patient, okay? Or equivalently, it's the largest average response across all the patients, because I give each patient a different treatment, and I give the optimal one for each patient, then it's going to give me the largest average response, because every patient is optimal. Okay? The goal for me is to find that subset of variables, let's say x sub s, that gives me a rule that has the same average response as the optimal one that I could have gotten if I used all of the information. Right? So if I used all of the x, I'm going to have an optimal rule based on using all the possible information. I want to find essentially the smallest subset that gives me the exact same average response as I would get if I used all the information. Those are the only variables that are relevant for decision making. Okay? And again, it's different than looking at prediction error. It's looking at, I want to find the subset that gives me the best rule. Okay? So going back to this example, the decision rule here is simple. Right? If x3 is greater than a half, I give treatment 1, right? Because that's where treatment 1 is better. Otherwise, if it's less than a half, I give treatment 0. There's no dependence on x1 or x2 in that rule, assuming that this model is completely additive. There's no other terms in there, right? So if you think about this very simple model, the rule is if x3 is greater than a half. In general, and we'll see this tree again later, in general, it's going to be much more complex. You know, you look at a decision tree, you go down the branch, and if this value is greater than this, you go left, and if it's less, you go right, and you follow the branch down, and you end up in the bottom cell. That tells you, well, I assign this treatment, right? But either way, the question is, what are those variables that are important to do that? So what are the common approaches? So what have people done to do variable selection in these treatment rules? Well, for the most part, people do variable selection as usual. You do some sort of regularization, you do cross-validation, AIC, BIC, standard approaches to variable selection. The problem is that targets prediction error. It doesn't target the decision-making subset at all. Right? But if you don't think about it that way, it's like, oh, okay, what variables are important? I'm just going to use standard approaches in my model. The other thing you can do is, thinking back to those pictures that I showed, you can include interactions between treatment and each of the variables individually, and you perform variable selection only on the interaction terms. So you look at which interaction terms with treatment are important. It's better, but it's still targeting prediction error, because the variable could have an interaction but not have what I showed before, what I termed you may have seen in the plot was called qualitative. Let me just go back just for a second to that. Yeah. So if you look, so the first one is no interaction. The second one is what's called non-qualitative interaction. So a qualitative interaction is one where, say, the lines cross, right? In the range that you're considering. So if I looked just at interactions, x2 would show up. So I might overselect things that are going to have interactions, but are still not important for variable selection, for decision making rather. Right? The other thing that people have done is they basically looked at those plots, just did everything univariate. Right? You calculated univariate scores based on do those plots, do they cross? Right? And then how much do they cross? So how much area is in the crossings? And then they rank variables based on those individual scores and then decide where to make a cutoff. That's probably what I've seen a bit most kind of progressive, because taking into account those kind of plots that I had, but you're looking at one variable at a time. You're not considering the model together. Okay, so the proposed approach that I talk about here is what I'm going to call no regret. And so the idea is I'm going to consider the regret, and regret is the term that's been used before to mean that I don't, well, formally it means the difference between what my optimal would be, okay? And so consider the regret from using that subset XS. So what I'm going to talk about here is I have a candidate subset. I'm not talking about an algorithm yet, but I'm talking about I have a candidate subset, and I want to decide how good is that candidate subset. Okay? So I've got a candidate subset X sub S, and I'm going to consider the regret compared to the full X. Okay? And I'm going to denote that as R sub S. So the idea is for every patient, I get, if I use the decision rule based on the full X, the optimal decision rule, I would get a response, right? The optimal response. Now, if I just have available to me this subset, I can try to find the optimal one for that subset, and I can look at what the optimized response is and compare them, right? That's basically the regret is, it's the difference in the average response obtained using the decision rule based on the full data compared to the decision rule based solely on the subset. Right? That's the regret, right? If I had the full data, I would do better, but if I only have a subset, I might be missing some important things. Right? So again, this is a theoretical quantity in a sense. It's not necessarily yet from data. This is a theoretical quantity. And the goal is no regret, right? I want to not have any regret. I want the subset to be exactly the same as if I had all the data, right? For decision making at least. So really what I'm talking about here is a formal hypothesis test on a univariate parameter, this RS, the regret, right? So that's where things are going to go, is it's going to be based on like a hypothesis testing approach for the regret. Okay. So let's go back to this simple case again. Right, so the decision based on the full model is if x3 is greater than half, give treatment 1, otherwise treatment 0. So let's think about what regret means here. I want to show, I talked about regret. Let's look at it, what it means in this case. So let's consider, I'm going to propose x1 and x2 are good, so I'm going to leave out x3. Okay. Then the decision rule is actually always give treatment 1. Right? If I only had available to me x1 and x2, then I have no knowledge of x3, but the decision is always give treatment 1. Right? So now what I've drawn in there, so if I had all three variables, x1, x2, and x3, I would look at when x3 was less than a half, I would give treatment 0. And if it's greater than a half, I would give treatment 1, which means my response is actually this V, right? Because when x3 is less than a half, I'm on this line, and when x3 is greater than a half, I'm on that line. That's the optimal decision, right? So the regret from throwing away x3 is the shaded area there. Because the response that I would get by just using x1 and x2 would be always give treatment 1, so I would be on that line. Right? So that my regret is that shaded area. Okay? If we throw out x1 and x2 and just keep x3, then I'm making the optimal decision. I have no regret. Okay? So x3 is the only variable, and so this demonstrates kind of that looking at the amount of regret, trying to show that it's 0, at least again theoretically, is a natural thing to look at. Okay. All right, well, the question now is, well, I want to conduct a hypothesis test. So in order to do some sort of hypothesis test, I'm going to need a model for the data. Right? I'm going to need something in there. So what I'm going to do here is we're going to basically use a flexible regression model. So given each treatment condition, I just want to do a flexible regression model. You can pick anything you want. The flexible model, so here I've got 2 treatment conditions. I've got A1 and A0. Just pick a flexible regression under each of the treatment conditions. I'm going to use the Gaussian process. This plot shows it marginalized out. I'll talk more about this plot later, but the idea is it's a Gaussian process that's marginalized out over all of the other covariates. This is just as a function of one of the 16 covariates in this data set. So I marginalized out everything else, but did a full Gaussian process. But you could do anything you want, right? The idea is I want to test this hypothesis of regret being 0, and so you could fit any flexible model you want to each treatment separately. Okay. So I'm going to do, and I'll explain why, depending on how much time I have at the end, I'll explain why I'm going to choose backward elimination here. Okay. And there's a very specific reason for doing so. But the process really is I do a backward elimination. So I have my current model. I estimate the parameters in the model. So if, in this case, I have 16 covariates. I'm going to do a full Gaussian process for treatment 1, a full Gaussian process for treatment 0. I estimate the parameters in that Gaussian process. For each patient, I now have predicted response for each treatment. Right? So I have a predicted optimal treatment rule for each patient, because I just decide which treatment is best based on my predicted values. I then remove one predictor, get a reduced subset, redo estimation under the reduced model. Okay. Using the 2 decision rules, I could get a directly plug-in estimate of the regret. Right. So just based on full versus reduced model kinds of ideas. I repeat for all predictors, like I'm starting with 16. I remove one, do that, remove another, do it, right? Standard backward elimination type thing. I look at all possible predictors to be removed, and I choose the one that has the smallest regret. Right? Because I want no regret, remember? So I try all 16 predictors. Which one can I drop with least loss? Right? And then I repeat until all subsets have a large enough regret that I don't want to throw any of them away. Right? Okay. That last sentence, I stop when I have a large regret. Well, what do I mean by a large regret? Right? Well, I'm not going to go into all the details, but R sub S, that regret for that specific subset, R sub S is a function of the parameters for the full model and the reduced model. Right? I should say R sub S is a function of the parameters of the true model. I'm going to estimate R sub S based on the estimated parameters. Right? Well, if I know the joint distribution, so it's just a function of the parameters in my fitted model, I can use the joint distribution, usually an asymptotic distribution. It's a transformation of that, and I could actually get a distribution of the test statistic. right? The test statistic is R hat sub S. And I'm going to use corrected p-values because I'm going to be choosing multiple hypothesis tests at each stage. So this is the data example that I had here. I'm comparing the two treatments, right? Both treatments are these combination treatments. I have 16 candidate predictors doing the backward elimination. It ends up removing 10 and keeping 6. Right? And the next one, if I decide to drop, so basically what's going to happen is so these are the ones that are left in the model. I've gone 10 steps. I've started with 16. I've thrown away 10. I've gone down. I've got these 6 left. If I went ahead and threw away each of these 6, each one is going to have a significant enough p-value that says, no, you can't do that. Keep it in. Okay? So these are the 6 that I found, like things where, how long they've been on previous treatment, an indicator of how symptomatic they are, the baseline cell count, and then you've got age, race, and indication of prior use. So things that seem to make sense about severity of the disease and then various demographic things. Okay. All right. So now what I'm going to look at is that plot that I showed before. I'm going to look at now what happens. So those were the variable selection. Now I want to think about how good is that method, right? I chose variables. How does it actually then perform in practice? If I use those variables to make my decision, how good is that decision? Okay? What I'm showing here first is those predicted or estimated response surfaces. So on the left is, again, I've got age, which is a univariate quantity, so I've marginalized out all the other variables in the model, and I'm looking at the age versus treatment, right? So there's 2 treatments. Each curve is a different treatment. And if you look at age, it looks like, well, this treatment is always better, right? The response is always better here. If I look at, this is whether or not they used this ZST within the last 30 days. Again, it looks like one treatment's always better than the other. So what happened there? Why are those variables showing up as important for treatment decision? So this is showing you, okay, if I look at each one separately, there's no importance of age or AZT use for decision making. So what happened? Why did my variable selection method pick out one of these? So if I would just look at these, there's interaction on this plot because they have different slopes, but they don't cross, so there's no decision-making relevance there. But actually, if you look at separating out age by whether or not they used ZST in the previous 30 days, then there's a difference, particularly here. Right? There's an interaction piece that for some reason, this region, they cross. When you look at age separated out by that second variable on the previous page. So the interaction between those 2 predictors. And what I'm showing here on the bottom is the distribution of age in this group to show you that this region has significant numbers of observations. Right? It's in this region here. So it's not like it's way out in the tail that it probably doesn't matter. There's a significant number of people there where maybe they'd do better from a different treatment. So maybe there's a subgroup that actually might do better from a different treatment. And so what I've done now is I want to evaluate what the proposed policy is compared to what if I just give other policies. So I'm going to do cross-validation here. So I'm going to just take, a whole bunch of, do 100 splits of the data. So I got a pretty good estimate of what's going on here. And so I'm going to calculate value of a policy. So the value of a policy basically is, what if I gave everybody treatment according to that policy? What would my expected value be? Okay, that's the value of a policy. And so it's averaged over 100 splits of the data. And basically what I'm looking at is compared to, so this one here is everybody treated with what's overall best. Right? On average, this is the best. So everybody treated, 100% of the people treated with that. And the value increase relative to the lower treatment, right? So this is looking at how much better this is than the lower treatment. It's basically 9.4 on the scale, and the 3.1 is the standard deviation. Right? Now, policy from SA, so SA, sequential advantage, was a method that basically looked at those univariate plots separately. So they looked at the univariate plots separately. Oh, I'm sorry, no, sequential advantage looks at selection on interaction. They looked at just looking at interactions, and I did selection, variable selection based on interactions. Okay? So I'm probably going to catch a lot of them, but I might catch things that are not quite relevant. And then RV is the regret-based, which is I'm talking about. And so if I use sequential advantage, about little over 50%, so in each case, a little over 50% got this treatment, but the rest actually got the other treatment, which was lower down. That subset was pretty significant, right? It was almost half the data are getting the other treatment. And I've got a very, very different increase in value, significantly there. I had 19 compared to 9. So basically, using selection advantage is pretty much the same as giving everybody the best treatment, the overall average best treatment. So that's a pretty significant result there. All right, now I've done this, but how am I going to implement this? How's a medical professional going to do this, right? I'm talking about, I'm fitting a Gaussian process, I'm doing this whole complicated thing. It's a black box to a physician. They're not going to want to put their patient characteristics into some computer and it spits out. I mean, nowadays they might, but in practice they want to understand a little bit more. So they may not appreciate just, here's a program, just put your patient's data in and it'll tell you which treatment to give them. They'll want to understand why a particular patient or have something there. And so what I've done next, and the tree that I showed earlier, I'm going to show again. Basically what I've done is I've taken the estimated policy here, and I'm going to provide just a friendly interface, something that the physician can actually just look at. And so basically what I have here is I basically do a grid, like a very large grid, and I have, which treatment is better on the grid, so I have a binary surface, basically, and I just constructed this decision tree based on that new data. So I'm using a decision tree to approximate this black box. And so what you end up having is something like this, and then the doctor can say, well, okay, my patient comes in, and they fall down, and I should give them this one. And so this is just an approximation to that full Gaussian process type thing. Right? I just want to finish off with, I said why I chose backward elimination. Okay? It's a little bit of a technical detail, but I'm not going to go through the technical details, but it's actually a key step in here. So 2 related questions you might ask. What happens when I have a large number of predictors? Well, backward elimination is probably not a good idea then. And why backward elimination rather than, say, forward selection, for example. Right? The first one is pretty straightforward. There's lots of ways to do screening. So you do kind of screen out the variables. You screen out the variables that are in each treatment separately. Anything that's irrelevant in both, means they're flat in both, then they're not going to be important for treatment. So you could screen out initially. The important thing is a bit more complex. So for forward selection, I have to add one variable at a time. Right? So I need to fit a model for each candidate subset when I add a predictor. So I'm at nothing in the model. I've got 16 candidates for my example. So I need to fit 16 models. Right? Need to do that at every step. The Gaussian process can be expensive to do that, even though you can do it in parallel, but it could be expensive. Okay, well, backward elimination, I need to do the same thing, right? I start at the top and I need to fit 16 reduced models. So what's the difference? Well, the difference is I could actually use an approximation to backward elimination. I could start with just the full Gaussian process fit. And then all the parameters are actually jointly normal, right? I can get the approximate distribution of that. Now, using that, I could actually approximate the results for any subset I want. And the reason for that is if you think about the range parameter in the Gaussian process, it's the effect of the variable on the expected value in that treatment group. So if I remove that x, it's equivalent to setting the range parameter in both groups equal to 0, right? It's the same thing. I set the range parameter to 0, it means it has no effect. Well, I can just then take the joint Gaussian distribution and condition on the fact that certain elements are 0. Well, many of us should know conditional Gaussian is, again, Gaussian with a known formula for mean and variance. So I actually get the distribution for any subset without actually having to refit anything. And I can use that in my analysis, which is why I chose backward elimination. Okay. And so I'll just stop here. The only thing I want to point out is some additional work that would be of interest is adapting it to time-varying treatment, right? I have multiple decision points, right? Which variables are important for which time point? What's the trigger to make a switch? There's lots more complication going on there. So that's kind of a thing of interest later.
Thank you.